Let's investigate the effect of distance on the force that two charges exert on one another to a greater extent. In the previous investigation, we did that. In that investigation, we asked, how does the inverse of the square of the distance between two charges affect the magnitude of the force between them? So what we did in that investigation was we controlled the magnitude of charge 1 and the magnitude of charge 2. We never touched those sliders. The thing that we made different between the treatments was the distance between Q1 and Q2. We started with them very close together, and we could see they were really attracting one another very strongly with a very high magnitude force. Then we moved them apart gradually, and each time we measured the force, and we saw that it drastically decreased in the beginning, and then later, as we got them further and further apart, the rate at which the force decreased slowed down. We found that force is inversely proportional to the square of the distance between two charges. Now, in this investigation, we're asking the same question, except we're adding another context. So again, we're asking, how does the inverse of the square of the distance between two charges affect the magnitude of the force between them? But now we want to do this for two values of Q1, Q2. In the previous investigation, we controlled Q1, Q2. Now we want to do it for two values of Q1, Q2 and see whether the relationship is different for the two contexts. So this is the old data that we have. Remember that we increased the distance from 2 to 14 meters apart. In the first reading, they were right next to one another, their centers only 2 meters apart from one another. Then we moved them incrementally apart until they were 14 meters apart from one another. So unsurprisingly, the magnitude with which they attracted one another was much greater when they were close, and it got drastically less initially, and then the rate at which it got less decreased as they got further and further apart, telling us that distance and force are not inversely proportional, rather distance squared is inversely proportional to force. So we squared each of the distances, and that's how we got that data in that column. And then what we did was we got the inverse of the square. 1 divided by 4, 1 divided by 9, and so on. And that's what we got in this column here. And we found that this column's data was directly proportional to the force data. In other words, 1 over r squared and force are directly proportional to one another. So that's the data that we got when Q1 times Q2 was 3 times 10 to the power minus 8. Now we want to do the same investigation, but with a different Q1, Q2 value. This time, Q1 times Q2 must equal 1 times 10 to the power minus 8. So all the other information in the table is still relevant because we're still going to have readings for distance 2 meters apart, then 3 meters, and so on until 14 meters. And so the distance squared, of course, is still the same values, and the 1 over r squared values will still be the same too. All we need to do is to fill in the new forces for this situation where Q1, Q2 is not 3 times 10 to the power minus 8, but rather 1 times 10 to the power minus 8 Coulomb squared. So we open our simulation, and we are going to keep magnitude of charge 1 at 50 times 10 to the power minus 6 coulombs, and magnitude of charge 2 at 200 times 10 to the power minus 6 coulombs. So let's quickly check that Q1 times Q2 is what we said it would be. We open our calculator, 50 times 10 to the power minus 6 times 200 times 10 to the power minus 6, and indeed we do find 1 times 10 to the power minus 8. So we're going to change the distance of separation between the centers of the charges from 2 meters all the way to 14 meters. At 2 meters apart, the force is 25,2 newtons. There's a drastic decrease in force as we get them another meter apart. Now it's only 11,3 newtons. At 4 meters apart, 6,2 newtons. At 5 meters apart, 4 newtons. 6 meters apart, 2,8 newtons. 7 meters apart, 2 newtons. 8 meters separation, 1,6 newtons. 9 meters separation, 1,2 newtons. 10 meters separation 1 newton, 11 meters separation 0,8 newtons, 12 meters separation 0,7 newtons, 13 meters separation 0,6 newtons, 14 meters separation 0,5 newtons. Here we have the data in our table. So now we want to compare the trends that we found in the previous data with the trends that we find in this data. To help us with that, let's put the relevant parts of the tables next to one another. So we don't need the distance and the distance squared. We just want 1 over r squared in each case, because that's our independent variable, and force in each case. That's our dependent variable. So what do we notice? The first thing we see is that as 1 over r squared is decreased, the force decreases. And that's the case in both contexts. But for a particular 1 over r squared, the force is less for the first situation than the second. 25,2 is less than 75,6. And what's also very interesting, 25,2 times 3 is equal to 75,6. 0,5 times 3 equals 1,5. And so on. You can check the rest. Sometimes you will not find it exact. 4 times 3 equals 12, not 11,7. Remember that we do have quite a bit of experimental error here, because to position the particles exactly at the right place within the simulation is rather difficult, because 1 meter is shown as a very little space, a very little distance, whereas actually 1 meter is quite far. But in the simulation, it's little, and it's rather difficult to place the charge exactly at the right place with the center the number of meters apart as it should be. And so obviously for that one, I didn't place the charges exactly at the right distance. They should have been a little bit closer together so that the reading would have been 12 here. So you must just take that into consideration, that there is experimental error. So when you're looking for patterns, you need to round things off so that the experimental error doesn't stop you from seeing the patterns. But if you do that, you will see that the values of the force for the second context are triple that of the first context. And that is not surprising, because Q1 times Q2 is 3 times more in the second context than in the first. Here I have the full table again for the context Q1 times Q2 equals 3 times 10 to the power minus 8 Coulomb squared. And what you should do now is to plot the data of distance squared on the x-axis against force on the y-axis for this context, then use the same set of axes and plot this data, which is for the context Q1 times Q2 equals 1 times 10 to the power minus 8. So again, you will plot distance squared against force. When you do that, you should get this graph. We get the shape of inverse proportion, and we get 2 lines. One is for the context where Q1 times Q2 equals 3 times 10 to the power minus 8 Coulomb squared, and the other is for the context where Q1 times Q2 equals 1 times 10 to the power minus 8 Coulomb squared. Which line refers to which? And how can you see that? Then you should also give the heading for this graph and label each of these axes. What is our independent variable if we plot the graph of this data? I hope you said square of distance between charges is our independent variable, unit meter squared. And I hope you said that the dark green line, the upper line, is for the greater value of charge, 3 times 10 to the power minus 8 Coulomb squared. And the lighter green line, which has lower values of the force, is for the lesser value of the product of the charges. And that's because the greater the product of the charges, the more force they exert between one another for a certain distance. The dependent variable is the force between the charges in newtons, or more exactly, the magnitude of the force between the charges. But obviously on the graph, we are showing magnitude. We cannot show direction on a graph. So we might leave out magnitude of. The heading is graph showing the effect of square of distance between charges on the magnitude of the force between the charges for 2 values of Q1 times Q2. Now let's get back to our tables where we summarized the data so that we could put the 2 tables, the 2 contexts next to one another. Then we didn't include distance and distance squared. We just had 1 over r squared and force. And now you should plot a graph showing 1 over r squared against force for each of the 2 contexts. Is this the graph that you got? Now the graph is a straight line. What is the independent variable now? Also, which context fits with each graph? What's the heading of the graph? What are the labels of the axes? Again, the dark green line, the upper line, refers to the greater product of the charges because it shows a stronger force for a particular distance. And you'll get a stronger force for a particular distance when the product of the charges is greater. Now, the independent variable is not square of distance between charges, but inverse of square of distance between charges, 1 over r squared. So the unit is not meters squared, but meter to the power minus 2, the inverse of meter squared. The dependent variable is again force between charges, unit newtons. The heading is graph showing the effect of the inverse of the square of distance between charges on the magnitude of the force between the charges for two values of Q1, Q2. So what is our conclusion? Again, we see that force is inversely proportional to r squared, which can be seen as force being inversely proportional to the square of the distance between the charges, or force being directly proportional to the inverse of the square of the distance between charges. And those two things are the same. It's just two different ways of saying the same thing. Now we know that in direct proportion, as the independent variable is increased, the dependent variable also increases by the same factor. For example, the independent variable might increase 5, 10, 15, 20, 25, and the dependent variable correspondingly increases 1, 2, 3, 4, 5. We can recognize direct proportion by dividing one by the other and getting a constant. For example, here we might divide independent variable by dependent variable and end with a constant, in this case 5. But what's important to realize is that we could do it the other way around. We could rather do dependent variable divided by independent variable, and we would also get a constant. All I've done here is I've swapped the position of the dependent and independent. Instead of going 25 divided by 5, I'm now going to go 5 divided by 25, and I get 0,2. 4 divided by 20 equals 0,2. And so I can go on. So we can detect direct proportion either by dividing independent by dependent or by dividing dependent by independent. We'll get a different constant depending which one we have at the top of the fraction and which one at the bottom. But it doesn't matter. It doesn't really matter what the value of the constant is. It's just if we see there's a constant, that tells us direct proportion is there. So in this case, we want to see whether the dependent variable force is directly proportional to 1 over r squared, where 1 over r squared is the independent variable. So to check if that is the case, we must divide one by the other and see if there's a constant that we get. So we're going to divide force by 1 over r squared. And if we get a constant, then we know that force is directly proportional to the inverse of r squared. Now force divided by 1 over r squared is equal to what? Remember, when we divide by a fraction, we tip and times. So force divided by 1 over r squared becomes force multiplied by r squared. Force divided by 1 over r squared is the same thing as force multiplied by r squared. And if the relationship is indeed direct proportion between force and 1 over r squared, this should give a constant. So let's check that. So we add in another column to our tables. Force times r squared. 4 times 25,2. 9 times 11,3, and so on. You need to complete these two columns before you continue with the movie. And this is what you should get. What do you see? Now again, if you look very strictly at the numbers, you will see that there's no constant in that column. There's no constant in that column. But remember that we have experimental error in this data. And so we need to round off so that the experimental error doesn't stop us from being able to see the patterns. If we were to round off to 2 significant figures, which is all we can actually do given the degree of precision of our data and our simulation, then we get these values. Force times resistance squared equals a constant of 100 for our first context and 300 for our second context. And what do you notice about 100 and 300? Of course, 300 is 3 times 100, just as 3 times 10 to the power minus 8 is 3 times 1 times 10 to the power minus 8. So let's add another column into our tables. And let's take that constant, F times R squared, and divide it by the product of the charges. F times R squared divided by Q1, Q2. So 100 divided by 1 times 10 to the power minus 8 equals. And 300 divided by 3 times 10 to the power minus 8 equals. And what do we see? Now we get the same constant no matter what the product of the charges is. And we could go and do it for more than just these two contexts. Get many different contexts of Q1 times Q2 and vary R squared, measure the force, multiply force by R squared and divide by Q1, Q2, and we will get the same constant in all cases. Now remember, we do have a lot of experimental error in this investigation, in this particular simulation we're using. So we have found that the constant you get when you multiply force by R squared and divide it by Q1, Q2 is equal to 1 times 10 to the power 10. Put in numbers, that's 10,000, 10,000 million. But in fact, if you could do this really very accurately, you wouldn't find the constant k, the general constant k that is, that applies in all situations, to be 10,000 million. You would actually find it to be a little bit less, 9,000 million. 9 times 10 to the power 9. And this is a universal constant. And this equation, F times R squared over Q1, Q2 equals k, where k is 9 times 10 to the power 9. That is called Coulomb's law. It's a law that applies whenever we have two charges, no matter what their distance of separation is, no matter what their charges are. So we can use it to calculate any of the unknowns. If we know 3 of these values, we can calculate the unknown value. Usually we rearrange this to make force the subject of the equation. Can you see that this rearranges to be force is equal to k, Q1, Q2 over R squared. Notice that from the first equation, what we're doing is we're dividing both sides by R squared. So it cancels away from the left, and we introduce it now at the bottom of the fraction on the right. And then we're multiplying both sides by Q1, Q2. That gets rid of it on the left, and it introduces it on the top of the fraction on the right. And that's how we rearrange to make force the subject of the equation. Force equals k, Q1, Q2 over R squared, where k has a value of 9 times 10 to the power 9. And this equation is called Coulomb's law.